Good morning, everybody, and welcome to today's webinar. My name is Cheryl Jennison DeProsa, and I'm joined today by Gino Sigismondi and Sam Drazen, and we are going to be discussing networking basics for audio professionals. It seems that IT networking is becoming more and more relevant for audio professionals, and this is sort of your crash course to get you up to speed and help you understand a little bit about how that interacts with your world of audio. But before we get into that, 2 items of housekeeping. This webinar is being recorded, as they always are, and it should be available within the next week or so. You can always go to shure.com/training to find all of our archived webinars. We have a lot of them across a wide variety of topics, all sort of related to audio. So shure.com/training for our archived webinars and for this one. And then in addition to that, as we go through today, if you have any questions, please feel free to type those into the question pane. We will answer questions at the end of the session, so please be patient. If you don't see the question pane, look for a little toolbar in the upper right-hand corner of your screen. And on that toolbar, you see a little orange box with a white arrow. Click on that, and that will maximize the little toolbar to get you to the question pane. So ask those questions. We'll get to them at the end. That wraps up all the boring stuff. Let's get into the interesting stuff. Take it away, Gino and Sam.
All right, great. Thank you, Cheryl, and thanks, Sam, for joining me here this morning.
Happy to be here.
Yeah. So this is going to be a fact-filled hour here. We're going to try and get through a whole bunch of stuff, but we're going to try and keep it focused. If it's not obvious from the title, Networking Basics for Audio Professionals, it should hopefully be understood that you're not going to come away from this webinar ready to be a Cisco certified network engineer, which is something that takes weeks, months, years of study to actually get there. But that's not our goal for today. But our goal for today is to help you as an audio professional be able to successfully install networked audio products, because that really is where, I won't even say the wave of the future anymore. It's where we are now. A large percentage of Shure products have an Ethernet jack on them and are meant to either live on their own network by themselves or as part of a larger corporate network. And that's where a lot of this knowledge really becomes important, because hopefully at the end of today's webinar, you'll have the words and the tools to be able to communicate effectively with an IT professional. So we want to help bridge that gap a little bit. Figure we'd start by defining what a network is. You hear that word used quite often, and a network is 2 or more like elements working together to solve a problem. In other words, if the network is not helping you solve a problem or helping you do something better, then it's not a successful enterprise. It's not a successful network. So that's really all that a network is, but we're talking about a very specific kind of network, which is an Ethernet network. To be successful, a network requires specificity. That means things need to be exact. So when we start talking about things like IP addressing and subnets and things like that, that's where the specificity really comes into play. Because if you don't have those items being as specific as they need to be, then once again, the network doesn't work. There's not a lot of room for sloppiness. It has to be specific to work. So here's what we're going to talk about. We're going to start out with looking at hardware and standards that relate to Ethernet networking, and then get into the meat of IP addressing, which is where a lot of this being successful and being specific really comes into play. We'll take a look at networking your computer. If you're going to successfully configure some of these networks, you have to make sure your computer is talking to the network correctly, and then end up with a little bit about networked audio specifically. So most of the first group of topics relate to Ethernet networks, whether it's data, audio, whatever, it doesn't matter. Those things all apply there, but there are some sort of extra considerations that you need to think about when you're working on an audio network. So hardware and standards. In this section, we'll cover transmission methods that are used in Ethernet networking, and then we'll talk specifically about hardware in relation to cables and connectors, switches and routers, which are the backbone of the system, and the bandwidth associated with that, and then a little bit about the topology of your network. So transmission methods. There are basically 3 methods of transmitting messages across a network, and we'll look at all 3 here. So you have a device that is doing the transmitting, represented by the blue square here, and then the red circles are devices that need to receive a message on this network. Unicast is the most basic to understand. It's uni, meaning one, so it's a one-to-one transmission method. I need to send this message to one device, which has now turned green, and that device has successfully now received that message. So that's good. It worked. It's very efficient from a network standpoint because you're not flooding the network with a bunch of information hoping that the right device gets the network, or having a bunch of devices that or message, or having a bunch of devices that didn't need to receive the message receiving it. So one-to-one is a very simple method of transmission there. Multicast is when you have the signal sent to multiple devices. So not all devices on the network need to receive a message, but several of them do. And you could actually do something similar with unicast. You could actually set up 3 independent unicast flows to have these 3 devices get the message, but that's not very efficient from a network standpoint because that same message then needs to be duplicated 3 times. In multicast, the information is sent once, but it's sent to any device that is subscribed to it or needs to receive that information. And then broadcast, just like broadcast television or broadcast radio, is one signal that is put out that can be received by any devices. So an analogy here might be, again, to go back to broadcast radio, right? You have, a FM radio station putting their signal on the air from a single tower, and everybody driving around in their cars can receive that signal. That's what a broadcast message is. From a networking standpoint, this is probably the least efficient way to go because it's just, I'd use the word flooding, but putting all this information out on your network for all the devices in order to receive it, whether they are subscribed to it or not. Again, multicast, the device has to kind of be expecting to get that information, but in broadcast, everybody gets it. So one to all. All right, so that out of the way, let's look at cables here. Just like in an audio system, an analog audio system, networking is really no different in that probably 90% of issues in a network can be solved by looking at cables and connectors. We've seen many cases so far in helping customers troubleshoot here where you spend hours poring over IP addresses and looking at all these other issues with your computer when it really turns out cable wasn't quite plugged in all the way. Maybe there's cable was compromised in some way, and you really do need to check all that out. In fact, the confusing thing about it sometimes with networking is you might have a device that looks like it's working and the lights might be flashing, and it seems like, oh, well, I see lights flashing, the cable must be good. That's not always necessarily the case, though. So it's always a good idea to confirm that. Most of the time these days you're dealing with Cat5e or Cat6 cable. Again, the differences there you can kind of see is that the crosstalk performance gets better as you move up with the different cable categories, and that then allows the cables to handle faster network speeds. So since almost every network that we're doing, particularly if we're talking about audio networking, is going to be a gigabit network, you're probably always using at least Cat5e or Cat6 cable. But notice the length doesn't differ. So that's the standard sort of cable, maximum cable length for an Ethernet network is 100 meters or about 300 feet or so. Anything beyond that, you need to add additional hardware to go longer than that, switches or whatever. But a straight cable run cannot be longer than 100 meters, no matter which type of cable you're using. Again, the E in Cat5e stands for enhanced with the more stringent crosstalk requirements and being able to use it on a gigabit network. And then, of course, Cat6 actually allows up to 10 gigs, more stringent crosstalk, but backwards compatible. In other words, if it's only a gigabit network, you can still use Cat6 cable. There's no problem there. When you look at the connectors, again, it's a RJ45 is the standard connector used in most Ethernet networks. It's an 8-pin connector. And then there's also a shielded variation too here, which is kind of obvious because the outer casing, instead of being plastic, like in our first example, is metal. That's a pretty good indication that is a shield cable. This is often required for networked audio and some other specialized applications. Generally, it's not a bad thing to use a shielded cable. Anything that keeps outside noise from being picked up by the cable is a good thing. And again, on an audio network, it's that sort of signal integrity becomes much more important than on a data network, because on a data network, when it's just information being sent, if there's additional if packets are dropped and there's additional latency, it's fine. It just means, the picture of your kids that you're trying to send someone over email. It just gets there a few milliseconds later. But in a real-time audio network, if the signal is compromised, then packet loss can actually cause drops in the audio. So again, is it always required to use shielded connectors on these networks? No. Is it a good idea? Most of the time, the answer is yes. So that's connectors again. Oh, and one more thing on connectors. I want to go back. The little tab that you see there at the top of the connector, it's kind of a plastic connector most of the time. This is probably one of the major culprits in the failure of a network connection. Again, we talked about checking your cables and connectors, how important that are. If that tab is missing, that really decreases the connector's ability to stay locked in place, and it can easily come loose. And again, it can look like it's in there. You might even still see lights blinking that make you think it's fine, but anytime you see a cable with that tab broken off, replace it. Okay, so switches and routers, this is the backbone hardware of the system that all of your cables and connectors connect to get all your devices communicating with one another. And they are not all created equal. As we note here, they are both consumer and professional products, and like with many things in audio and other things, you do get what you pay for. The analogy we often use with people is when they're trying to choose a switch, maybe they ran down to the local electronic superstore and bought the cheapest one they found on sale because it had enough ports on it, and then they wonder why there might be some communication issues happening. There are compromises to be made, cheaper chipsets that can be used that can compromise the performance of a switch. So in a professional application, which is mostly what I think we're talking about here, using a professional network switch or router is generally considered a good idea. If you're going to hang $10,000 worth of professional audio equipment off of a $50 network switch, maybe you might have some issues that might otherwise be solved by using something a little bit higher grade.
Given all the features that some of these devices have too, it's very much the case with reliability and functionality that you get what you pay for. And not that you need to buy the most expensive switch or router possible, but this is typically one of those things that we see people hook up with designated power to a switch or a router, and there's a certain threshold of quality. I think you want to make sure that all your devices can communicate together.
Yep. There's other features you might want to be considering when you're looking at a switch. Wireless. If you need to run a control application from an iPad or a mobile device, then you would need a wireless router, for example. DHCP servers, which has to do with IP addressing. We'll talk more about that in a little bit. PoE is power over Ethernet. That's a big one. A lot of the audio devices that you might hang off of a network switch require power over Ethernet. They don't have their own power supplies at all. They can't plug into the wall. So PoE is a big one to look for there when we're talking about switches. The difference is that a switch is generally just used for connecting a group of local devices. So the little purple boxes could be wireless receivers that are networkable or something like that, but they're just kind of its own sort of little network. A router is used to actually route signals across networks. So you might have several switches connected to a router that then connect to another router that have another group of switches, maybe in another location, another building. But again, the router is generally used when you want to connect different networks together or to the internet. The internet is kind of a separate network. So if you need to get your devices out to the internet, you would go through a router, which would then manage that connection there. Kind of a high-level description, but that's sort of the basic difference there. And there are other types of switches too. We won't get into all that today, but basic level. All of this network hardware, of course, has bandwidth associated, which is, you think of bandwidth as a pipe, and a pipe is only so big, and you need a pipe that's big enough to fit enough information or data or bits or whatever it is that you're trying to get there. So it refers to the speed at which the data can travel. And again, all network devices have a certain rating associated with them. Most common you see today are either a 100 megabit network or a 1,000 megabit or a gigabit network. And in almost every case, just speaking kind of about Shure products specifically for a minute, you're going to be looking at a gigabit network. It's just a more reliable, especially when you have a networked audio traveling on there. It's best to just kind of go with that gigabit network, and you'll have increased reliability there as well. And just a couple quick notes then on topology here. So there are a number of different ways that you can connect your network together from a topology standpoint. What we're looking at here is what's referred to as daisy chain topology. So these are the back of ULX D4 quad receivers, which have 2 network ports on them, labeled primary and secondary, which is actually a Dante thing that's not necessarily relevant because the way these devices are kind of configured in their default state is as a 2-port switch. So we saw a photo of like an 8-port switch earlier, or picture a 2-port version of that built into the back of these receivers. So when it's working as just a switch, that means that you can use either port to plug into, and you can daisy chain from one to the next. The important thing is you just don't want to have a loop, right? So you wouldn't loop back from the bottom receiver to the top receiver. A network loop is always a bad thing and causes all kinds of problems. But assuming there's no loop here, this is a fine way to connect your devices. Everything works just great. Again, there's not like a whole bunch of latency added because you're daisy chaining. It works fine with one possible exception. And that is, if anything happens to that one cable that is daisy chaining to additional receivers, well, that means that you lose everything below it. So if the cable between our second and third receiver gets unplugged, gets compromised, we haven't just lost that one receiver, we've lost every receiver below it. So though, again, you don't need any external hardware here. There's no external switches needed. It's very simple. For a small number of devices, maybe it's okay, but you should be aware of that. In a star topology, this is really kind of the preferred method if you have the additional hardware like the D-Link switch zone here to support it, right? Which is now this computer has essentially a direct connection through the switch to all of my devices, so that even if one of the cables gets compromised, I do lose that one device, but I haven't lost my connection to everything else. So in general, star topology is kind of considered the preferred method for networking your hardware together. You may not always have the choice depending on whose network you're connected to, but that's kind of the way we like to go. So moving on to IP addressing.
So Gino introduced some concepts like cables and switches and routers. I like to think of those in an analogy when it comes to networking like neighborhoods and houses. If cables are the roads between houses and switches and hubs, or switches and routers are like the intersections between the roads, IP addressing is like the address that each house has. And it's an important concept because in a network that requires specificity, when one device wants to send a message to other devices, specificity is going to be what ensures that the message gets to the right place. And IP addressing is probably the most common thing that users end up having to encounter and needing to configure appropriately to make sure that the specificity can be there in a network. So just some quick definitions about terms that live in this world. There are things like MAC address, IP address, subnet mask, and gateway, which we'll discuss. And then we'll dig a little bit deeper into how to set up IP addresses. There are a couple different methods that you can use, whether it's dynamically or statically giving out IP addresses. And then some methods that help to assign IP addresses in a dynamic setting. And then we'll also touch on some port configuration. Again, if these terms are foreign, we're going to explain all of them in a little bit more detail. So the first term to explain when talking about networked appliances is a MAC address. You can think of this like a social security number for a network device. And a sample one, sort of a bogus one, is listed down there below, but it's split up into these 6 groupings of characters. Each one of those characters is a hexadecimal character, or between 0 and 9 and A and F are the allowable characters. This is an IEEE standard that provides a lot of different unique possibilities, but what you need to know about it is for every networked appliance, this is a unique value. And actually those first 3 pairs of characters are actually manufacturer specific. So if you look at the MAC address for a number of different devices from the same manufacturer like Shure, you'll see that they all share those first same 3 pairs of values. And then the last 3 are used to uniquely identify different devices. At the lowest level, when network devices are talking to one another, it's this value that helps the network uniquely identify one device from another.
I like the Social Security number analogy because that's a number that is assigned to you basically at birth and stays with you your entire life and will not change and is unique to you. And the same thing with the MAC address. It is assigned to this device at its birth, essentially, programmed ahead of time at the factory, and it doesn't change. MAC address always remains the same.
So the next attribute we'll talk about is the IP address. And an IP address is different from a MAC address. Well, it's the same in that all networked appliances have an IP address on a proper network, but the difference is that an IP address can be assignable. It isn't built in at birth and totally unchangeable. You can think of this like a device's address on a network. Its format is a little bit different. It's comprised of 4 numeric values, or we'll refer to them as octets. Each of them is typically represented as a number between 0 and 255. And there needs to be specificity and specifically uniqueness for an IP address for any device on a particular network. So back to the neighborhood analogy, you can think of this like if Gino lives at 123 Main Street and I live at 456 Ashland Avenue, the mailman or any packages sent between us can know specifically which house is Gino's and which house is mine. This just helps messages get to the right place and know where the right destination is for a particular message. So you've probably seen a really common IP scheme like 192.168. This is a very common IP range that is automatically assigned to devices by routers. And one thing I want to call out here is we're using this word subnet. Subnet is a definition of, you can think of it like a neighborhood. And the reason this concept is important is Gino might live at 123 Main Street, and in another city somewhere else there might be another 123 Main Street, another address that has the same value. That's totally fine and appropriate, but what matters is that per neighborhood or per subnet on an IP network, there can only be one appliance at each IP address, and that's how messages know to get to the right place within their given network. So we talked about a subnet, but I want to define it a little bit more specifically. A subnet is an entity that subdivides a network to a range of IP addresses. And this defines the scope of a neighborhood. Basically, within a subnet or a local network, all of the IP addresses on that network need to be unique. And messages can flow freely between those devices. An example of a subnet, you can think of it like a local network of devices you might hook up straight to your computer. It's just one contained network, and it doesn't necessarily have access to other networks. In some further slides, we'll discuss examples where multiple subnets or multiple networks can be joined together, and messages between them can be sent through a router. So we talked about IP address, we talked about a subnet. A subnet mask is another value that's associated with the definition of an IP address, and this defines how many usable IP addresses or hosts there are in a particular network. So typically when you're configuring devices and their IP addresses, you'll see IP address and subnet mask. Those are peanut butter and jelly, always right next to one another. And the reason that is because the 4 octets of a subnet mask are what specify how many different IP addresses and which octets of the IP address are allowed to be unique and must be the same. So similarly to IP address, there are 4 numeric octets, each typically 255 or 0. There are some exceptions we'll show in a second. But let's apply these two and see with a particular subnet mask which IP addresses can there be on a network. So this is just a quick picture of one little local network where all of the IP addresses of the device have their last octet unique, and through a switch, a device at 192.168.145 can send a message to 144. So kind of stepping into how you define the scope of a network, subnet masks are used to basically open up certain octets for there to be uniqueness amongst the IP addresses. So typically what you'll see are one of these 2 examples of a subnet mask, where the first 3 octets are 255 and the last one is 0, or the first 2 octets are 255 and the last 2 are 0. And if we apply these to an IP networking scheme, I know this sounds a little bit abstract, but basically, if you, depending on how many devices you have on a particular network, this is what would lead you to choose one subnet mask versus another. So if I had the subnet mask 255.255.255.0, then it would allow me to have the following IP addresses as legitimate IP addresses on the network. You'll notice that these first 3 examples all share the exact same IP address octets, the first 3, all 192.168.1, and then the only variation in the IP address corresponds with the same octet that is 0 in the subnet mask. So you'll notice the last octet of the subnet mask is 0, and therefore the last octet of all the IP addresses is unique. Now this 4th one violates that rule. because the third octet is expected to all be the same across all IP addresses, but this fourth IP address is different. Instead of 001, it's 002. So if I had 4 devices with these IP addresses on a network, that fourth one wouldn't be able to communicate with the other 3, and vice versa. Another common example when devices have their own, when are on a link local network, which Gino will explain in a moment. Here's just another example to illustrate the same point. If the last 2 octets are open of the subnet mask, and by open I mean set to 0, which is a sort of signifier of allowing variation in the IP addresses, you'll notice that the first 3 addresses can vary in their last 2 octets. And then the fourth IP address varies in the second one, which is specified to all be the same. And because of that rule, the fourth address wouldn't be able to communicate with the first 3. So these are just visual examples of how subnet mask and IP address work together to specify the allowable scope of a network. You can also notice the more octets that are open, meaning if just the last octet is open, then there can be roughly 250 odd IP addresses. And if you open those 2 last octets, then there can be roughly 250 squared IP addresses. A lot. So just to give some practical examples about subnet masks, subnetting or using different IP subnet masks changes the number of IP addresses or hosts allowable on the network. Now I mentioned typically you see these values either as 255, which is closed, or 0, which is open. There are some variations. Maybe in a later webinar we'll talk more about why you might use different subnet mask values to change the number of hosts, but just a quick table to show you, based on the value you specify, how many hosts there are allowable on a given subnet.
I like to add here that this is one of those areas where if you don't know what you're doing, you probably shouldn't be and should be consulting with an IT professional.
That's a good point for basically every aspect of this presentation, I think. There's a lot that gets pretty complex. So some examples of subnets. I mentioned an example of a local network earlier, typically just one subnet. This is a smaller, self-contained network of gear. It could be just a rack of wireless receivers you have connected to your computer. All of these devices are addressed within one IP range, and any basic router or switch configuration is usually fine for this sort of network. It's the distributed networks or the larger networks that often occupy multiple subnets. They're a bit more complex. These are larger. They tend to be distributed either across geographic locations or by types of gear. Subnets tend to divide and organize devices into separate IP ranges. So you could imagine if we were running a bunch of networked gear for a college campus. You could imagine the West Campus and the East Campus being unique subnets, but all routable within the same large network. Typically, these distributed networks require layer 3 switches and routing configuration to allow the subnets to talk to one another. That's definitely a topic beyond the scope of this webinar, but something you should be aware of. So just some really quick examples. A local network can probably be found either on a touring rig or a small installation, maybe a house of worship. The picture I have on the right is just a rack of Shure wireless gear with a computer connected to it. And this is the beginning and the end of the network. All of the gear is self-contained right here. The benefit of this smaller local network is that connecting these devices together is relatively easy. There are no external constraints about IP addressing or fitting into a larger network scheme. You can kind of do what you want. And a lot of the software that Shure builds leverages this small network by being able to plug right in, automatically discover all the devices, and things are relatively plug and play. On the contrary, an example of an enterprise network or a distributed network, it gets a little bit more complex. These can be seen at educational campuses, large government facilities, corporations or corporate enterprises, even multi-venue studios. This is where different logical groups of devices, this picture I have on the right shows them as geographical ranges like campuses, but the same could be said for audio equipment, lighting equipment, powering equipment. These different subnets or different networks require a little bit more configuration and connecting the devices to one another and then to a centralized router that enables traffic to flow between these subnets is a little bit more manual, and you need a little bit more savvy to get things set up properly.
Okay, so now we know what IP addresses are, and we know that they have to be unique and specific for our network to be successful. So let's talk about how do you get an IP address? There are several different ways: static, automatic using link local, or DHCP. and DHCP, in case you're wondering, stands for Dynamic Host Control Protocol. If you're wondering what that acronym was for. Lots of acronyms here. So there's really the two different ways, but within the two different ways, automatic has a couple of different variations in it. Static, the word static should pretty much define what that means. It's an IP address that does not change. So it's manually assigned and will always be what it will be. Of course, automatic means that it happens automatically. You don't have to do anything about it. So just about every network device that you're going to encounter today, I can say that for certain for Shure network devices, supports DHCP or automatic IP addressing. And what that means is that if you are connected to a switch or a router that has a DHCP server, and it is enabled, because often those things can be disabled, but if it's enabled, then that means your device, when it will receive a broadcast message actually from the DHCP server saying, hey, would you like an IP address? Yes, I would. And you get an IP address. And it very commonly looks something like 192.168.1. something. It doesn't have to be, but that is a very commonly used IP address scheme that you'll see coming out from a DHCP server. And more often than not, the default subnet mask is going to be that 255.255.255.0. So that means this DHCP server has 254 possible IP addresses that it could send out, right? So for a small network, basic DHCP server like this works great, and it's easy, particularly for those of us who may not have, very high-end networking skills, to just get a bunch of devices talking to each other. You know that if you're using a DHCP server, every device will receive an IP address, and that it will be unique, and that all these devices will be able to talk. It's pretty much the no-brainer way to get your devices working with one another. Now, let's pretend that your devices are set for DHCP and they're looking to get an IP address, but the DHCP server on your switch or router is off, so it's not currently handing out IP addresses. Well, then what happens? Well, in this case, the device waits, and depending on how long it waits is kind of a little bit unique for a device, but it waits a certain amount of time. And eventually, if it says, well, I guess I'm not going to get an address, it defaults to what's referred to as a link local address. And this will always follow the scheme you see here, which is 169.254.something.something with a subnet mask of 255.255.0.0. This is a unique IP address because it's actually derived, those final two octets are derived from the MAC address. And remember, the MAC address of the device is unique, pre-assigned at the factory, will not ever change. So that means that if you have a group of network devices all set for DHCP automatic and they don't find a DHCP server, then guess what? They all fall back to this link local address scheme, and they all find each other and work together just great. So this is, again, a simple way to go. It's maybe not quite as robust as when there's actually a DHCP server there, but for the most part, this works just great. Your computer does the same thing too. If your computer's network adapter is connected into a network and it's set to obtain an IP address automatically, and it doesn't get one, then it will also come back to this 169.254 address. So whenever you see those addresses, that is almost always going to be this link local address. Now, I have seen people sometimes choose to use this scheme for static IP addressing. I don't think that's necessarily the best idea, because then it's hard to look at the IP address and necessarily know, oh, did I statically assign this, or is this link local? I don't know. So something to, again, kind of a little best practice to keep in mind there. So, static IP address, again, this is where you go in and you manually assign IP addresses. Why would you choose to do this? Well, in terms of specificity and predictability, it's as specific and as predictable as you can be. With DHCP, there is always the risk that a device IP address might change. When you cycle power on the device, it comes back on, it requests a new IP address. It's going to get a valid IP address, but it might be different than what the device had before. So when you care very specifically about making sure that your devices have an IP address that will always be the same IP address and it will not change, static IP addressing is the way to go. So it's very stable, very predictable, but you have to be very careful. Again, duplicate IP addressing is one of the biggest gotchas that we see in helping people troubleshoot networks here. Something's not working, the network's being goofy, you dig down far enough and you find, yep, here's two devices that have the same IP address. Yeah,
this is a really good example of something where it's good for you to know whether you need to know the IP address of your device. Every device having a unique IP address is really a means to an end. And depending on maybe the software that you're using or the communication patterns between the devices, oftentimes you don't need to know which IP address your devices are running on, as long as you've got access to control and interact with them as you need. It's only in certain cases where you need to log into a particular device or launch a web interface or something. If you have one of these applications where you need to know which IP address your devices are going to be on always, then this might be for you. But otherwise, using DHCP is not only an easier method, but I think I would almost say we recommend it in that it's foolproof in a lot of cases. You take a lot of variability off of the hands of the installer or the integrator and just let the machines do what they're good at.
And the final reason here says, of course, because you have to, right? I mean, again, if we're talking about integrating audio products or video products or whatever you happen to be doing on an enterprise network, a lot of times you're going to be told, here's the IP addresses you have to use, and you can't use any others. So it's an important consideration. Real quickly, just so that we can define it, we're not going to have a lot of time to get into specifics here, is what is a VLAN? You hear that term thrown around a lot. If you didn't know, that's virtual local area network. And the concept with the VLAN is with often maybe even just one switch, even though it looks like one network because everything's connected to one physical switch, you can actually subdivide that into several virtual networks within that switch. And larger organizations will often use VLANs as a way to extend the network maybe outside of the building to allow people to work from home or whatever is another application of a VLAN. So in this audio VLAN here, each of the different colors represents a different network. So you can kind of break things down. So for example, here we've got just a couple of our power amps and a computer on the yellow network, and then the ones that are on the green network are on a different network. So again, it's just a way of subdividing a network, and perhaps in level 2 we'll get a little bit more into VLANs.
One thing just to add to this is that it should be debunked, the notion that you can just walk up to any switch that looks like this, plug in any device, and expect everything to work. In larger corporate enterprises or places where these fancy switches and routers are being used, a VLAN configuration like the one we're seeing on screen could mean that every port even is on a different VLAN with a different IP range, with all these different specifications. So you definitely want to contact an IT administrator if you're hooking up into a larger network.
You should always be contacting the IT administrator if you're hooking into their network, right? So speaking of, what to tell the IT department. So here's are the common things that you really need to think about when you're communicating with an IT department, when you're integrating onto a larger network. They're going to want to know how many physical devices you have. Separate from that, they're going to want to know how many IP addresses you need. And this is a really key one because it's not necessarily one IP address per device, specifically when we're talking about networked audio products. If you have any of our devices, Shure devices, that also utilize Dante, that device, not 100% of the time, but most of the time, requires 2 IP addresses, one for the control side and one for the Dante networked audio side. So how many devices, yes, and how many IP addresses might be a different number, and which ones need to be on which subnets. Sometimes, and often with a networked audio, the devices need to be on the same subnet. So which devices need to be on which subnets? A topology, cable topology map is also useful in this regard too, specifically when you're troubleshooting, right? And then finally, what IP address scheme are we using? Are we going automatic with DHCP? Are we using static? If so, what are the IP addresses that you need? All of those sorts of things are important in communicating with the IT department. To the point about how many IP addresses are required, this is getting a little Shure specific here, but within our FAQ, if you search for answer ID 5415, it will pull up this document that shows for all Shure devices the total number of physical ports on the device, how many IP addresses it needs, how many MAC addresses it has, what the network speed is, whether it has Dante, PoE, it's pretty much the complete network information about all of our devices. It's a good reference when you're planning out your network and when you're communicating with the IT department. What else to tell them? traffic for these types of devices is typically very low. When you're looking at just the control side where it's data only, it's 0.02% of a gigabit network. So really nothing to worry about there. And even with Dante, it's approximately 1.28% of a gigabit network, and that's a large Dante network. We're going to talk a little bit more about Dante kind of towards the end here, but just so you know, even with the Dante network, the amount of traffic that we're generating is very low. VLANs can be supported, of course, if the network is configured correctly. Ports and protocols, I'll talk about in a minute here. And then just a couple more Dante things here. It's important to know that Dante flows are unicast by default. So we talked earlier about the difference between unicast, multicast, broadcast. Dante flows are unicast. You can create multicast Dante flows if you need the same signal to go to multiple devices, but they're default by unicast. The reason this is important is because, especially amongst IT professionals, there tends to be a lot of misunderstanding about networked audio and Dante and what it means to have it on your network, and that, well, it's going to flood my network, there's going to be Dante traffic all over the place, everyone's going to hear it. It's unicast. So those flows are unicast. They're only going one-to-one, which is one of the reasons that it helps keep that traffic very low. P2P is required for clocking, so like any other digital audio, it's important for things to stay in clock sync, and that clocking requires P2P to be enabled, which is something, to get back to ports and protocols, that can be blocked on a network switch. That P2P protocol, if it gets blocked, is going to cause problems for a Dante network. And Dante Controller is a piece of software, if you haven't used it, that is useful with Dante networks because it has great error reporting that will show you if any of this goofy stuff is happening that might point back to something like PTP being blocked. Multicast is required on a Dante network for devices to be discovered, and again for that PTP clock in order to work. So even though the flows are unicast, if multicast is blocked on the switch, things can get a little bit hairy. All of this is to say is the IT department is often going to need to know what ports and protocols are utilized by Shure devices, or any device for that matter. If you're curious what they are for Shure devices, we have a couple of FAQs on this topic, searching for 4930 or 4618 on our website, or just searching network. Honestly, if you just go to the FAQ and just type in the word network, you'll see a lot of these things pop up, and it'll show you what ports we use, the protocols, the description of why that port and protocol needs to be there. So, for example, if you need to update devices on your firmware on your Shure devices and port 64,000 is blocked on the network, well, guess what? You're going to have problems discovering and updating those devices. So it's, and a port, I just think of it as a portal. It's a door, right? It's a door on the network. And if that port is closed, you're going to have problems finding your devices. So another good reference to keep in mind. Speaking of getting your computers on the network,
this next section really applies a lot of the concepts we've talked about earlier, and I think it's going to be reusing some certain concepts. So when you network your computer onto a network, it's typically to run some software or to log into a web interface from one of the devices on the network for controller monitoring purposes. So we'll cover a couple quick things: how to connect your computer to a network, what a network interface is and why it matters, and a little bit more about your computer's IP address. So first off, it really matters what you're connecting to. When you have a computer on your desk and you want to connect to either one device or multiple devices, the way that you would approach each of those things matters based on the number of devices. If it's just a single device, you can very simply plug an Ethernet cable into the device and an Ethernet cable into your computer. And as long as you ensure that both your computer and the device are in the same IP range, which can be done by modifying the IP address and subnet mask on one device or the other, or both, to put them on a known network, you can communicate with the device from your computer in very much this way. A network of devices is a little bit different, and we sort of think back to some common network topologies. Basically, the best way to do this is to have a star topology network, or a network configured where all the devices come into a switch, and then you can connect your computer to that switch. And the things you need to keep in mind are: make sure that the type of addressing for both your computer and all the devices is the same, so that IP addresses can be administered to both the devices and your computer. Remember, your computer is effectively another network appliance, same as a wireless receiver or any other networked thing. And then the last consideration you want to have is are you connecting your computer to devices standalone on a local network, or are you a part of a larger corporate network? If the former is the case and it's just a standalone network, you can be a little bit more fast and loose with how you address all your devices and hook things together. But if you're hanging off a corporate network, there likely are DHCP servers assigning IP addresses and rules for how networked appliances behave. So you want to be careful before plugging a bunch of your devices onto the corporate network and turning on maybe your wireless router as a DHCP server. You need to make sure that your network devices are following the rules of the larger network. That's definitely a go ask the IT guy sort of thing. So network interfaces, the network interface is basically a route through which your computer connects to a network. And our common laptops or any computers have a couple of these by default. Wi-Fi is an example of a network interface. A hardwired Ethernet network is a hardwired interface. And there could be others, Bluetooth adapters or Thunderbolt adapters. The point about knowing about your network interfaces is that to communicate with your devices on a network, you have to make sure you're talking through the right network interface. If you're hardwired connected to a bunch of gear, but you're trying to send commands through your Wi-Fi network, you're shouting out the front door while the kids are playing in the back, out back in the backyard. That's not going to work. They're not going to hear you so well. Last but not least, I think it's helpful to know how to find your computer's IP address. We talked about networking a bunch of devices on the same network and ensuring that they all have IP addresses that are sane and on the same network. And as I mentioned earlier, your computer is no different. So we'll go over quickly how to find your computer's how to find what your computer's IP address is, and then through the system preferences, you can change it to make sure it's proper if it's not. So if you're running a Mac, if you open the terminal application, you get a window that looks like the one on screen here, and you can type in the command ifconfig. And if you type that command in and hit enter, you'll get a printout of all the network interfaces that your Mac has access to. And the one we've boxed in green, I think is the wired network, if I'm not mistaken. And you can see in there's a bunch of information. But as a part of this package of information, the iNet, I believe is what it's called right there, is the IP address of my machine. And the, let's see, that's where the mouse is right there. And that's a helpful way to see, my computer's at 192.168.2.17. If you were running Windows, the same command except ipconfig is what you would type into the command prompt. You can get to the command prompt on Windows by typing cmd in the start menu and hitting enter. So you open the command prompt, type ipconfig, hit enter, and you'll get a similar response for your Windows machine as to what IP address your computer is. This is just a little bit closer up look of that. Now, if your computer's IP address isn't what you'd expect it to be, this is when you'd want to go into Control Panel on Windows or System Preferences on Mac. And in the network settings, you can then specify whether your computer is expecting to obtain an IP address automatically, aka DHCP, or manually specify an IP address such that your computer adheres to the IP scheme of the network you want to connect to. Here's an example of that Windows shot right there. And on Windows, it's a little bit more clear. You see IP address, subnet mask, and default gateway, which we didn't really discuss too much.
Okay, let's wrap up here with a little bit on networked audio and some specific considerations there. Again, networked audio is a way of allowing digital audio, multiple channels or multiple sources of digital audio to reach multiple destinations, often utilizing standard networked hardware. It doesn't have to be the case, but that's kind of where we've moved with protocols like Dante now, where it actually is basically utilizing a standard Ethernet network for moving this digital audio information around. Again, we talk about Dante specifically here because that's the protocol that Shure has adopted, as have many other manufacturers at this point, which allows these devices to communicate over this Ethernet network. It supports very high channel count with very high quality audio, usually on a gigabit network, very low latency. It is more or less plug and play. I won't say it requires zero configuration, but a lot of times it is just as simple as getting these devices on a network and letting them see each other. And it's important to understand that this works on a shared network. Dante does not require a separate network. More and more these days we're hearing requests from IT departments that want to set up the Dante network separate from the control network and everything else. Again, that is not a requirement. Dante was actually designed to be able to exist on the corporate network. Now, you might have other reasons, security-based or whatever, for not wanting that to happen, but from a bandwidth and usage standpoint, it actually works just great. The things I wanted to touch on here really relate to some specific, I think, best practices when you're putting Dante digital audio on a network. One of the most important things is making sure that you have a network switch that's up to the task. We spoke earlier about, the difference between consumer and professional grade switches, and of course, going for something a little more professional grade is typically a good idea. People often ask us for, well, which switch should I buy? We don't really maintain a list of switches that we think are good, because there are many that are, and it would be impossible to keep that list up to date. But at a basic level, you want to make sure any switch that you're using is, and really this goes even beyond just the audio network. For any of our Shure network devices, a managed gigabit switch with power over Ethernet is your basic level of things you want to look for. And we'll talk about why the managed is important in a minute. Of course, power over Ethernet is important because many of our devices require that, or they won't turn on if you don't have power over Ethernet on your switch. And gigabit, just that the higher bandwidth just makes the whole system more reliable and more stable, which of course is important when we're talking about real-time audio. You also want to make sure that you avoid what are sometimes referred to as green switches, or something referred to as energy-efficient Ethernet. It's IEEE 802.3.AZ. The concept there is that to be more energy efficient, which is a good thing, unused ports can be turned off or put to sleep by the switch. This is, again, problematic for a real-time audio network and can cause bad communication, clocking errors, packet loss. You really want to actually avoid that. And it's one of the arguments for a managed switch, because in an unmanaged switch that has green Ethernet, you can't turn it off, and that might cause problems. Managed switches allow you to connect to the switch and turn on and off certain features like energy-efficient Ethernet. Other considerations for Dante, shielded cable is, again, not a requirement. It will work without it, but as a best practice, it's generally a good idea to use shielded cable. Again, keep in mind what we said earlier about there possibly being multiple IP addresses per device, and kind of reiterating the Dante flows are unicast by default. Again, getting into some specifics about switch configuration, as I mentioned, one of the first troubleshooting steps you should take when you have bizarre or unexpected network behavior is turn off energy-efficient Ethernet on your managed switch. As I mentioned earlier, remember the Dante flows are unicast, but multicast is required for discovery and clock sync. So that's another thing you want to make sure is that multicast is not blocked or inhibited in any way on your network, because that will impact these aspects of Dante. And again, too much to get into in this webinar, but IGMP snooping, which it's Internet Group Management Protocol. This is a feature that a lot of switches have for more efficiently managing multicast traffic. And we have an FAQ on this topic. If you search FAQ number 5243, you can read all about it and what it means. But the important thing to note is that at a very high level is if you're on your own little self-contained network and you're not dealing with the IT department and your switch has IGMP snooping as a feature, turn it off. If you're on a larger network, you don't have that choice and you're consulting with the IT department. And if the IGMP snooping feature is not configured properly, that can sometimes cause issues for a Dante network, and it's something that you can read more about in that FAQ, but it is something that has become coming up more and more as you see these products integrated into larger networks, something to be aware of. So to kind of sum up here, I want to get into what I think are our top 5 issues that we run into with Shure applications engineering. We spend a lot of time, more often than not, troubleshooting network issues these days. And at a very basic level, here's some things you can check out that will solve a large percentage of the problems. Number 1, devices that need to be on the same subnet are indeed on the same subnet. They have the same subnet mask with unique IP addresses. This is a big thing. So many problems are solved simply by discovering, oops, there's a duplicate IP address out there, or oops, the subnet, these devices aren't on the right subnet. Like, just going through that, having all that organized and double checking that should always be step number 1. Step number 2 is if your computer can't find these devices, to the point of the things Sam mentioned earlier, right? Make sure your computer's on that same subnet. Again, a common call is, I got my computer hooked up to the network, I'm not seeing anything, and it's because your computer doesn't have the right IP address. It's actually not on the same subnet virtually. It might be physically by nature of the cable, but it's not actually set up in the way that you can find those devices. Make sure the following applications are up to date and allowed through your firewall: Shure Web Device Discovery, Shure Update Utility, Dante Controller, and Shure Wireless Workbench if you're using it for those devices that need it. Again, a lot of times, I can't discover my devices. Oh, you're using a version that's 2 years old. Or I can't find my devices because the device isn't allowed through the firewall. Get to know how to allow devices through your firewall. It really solves a lot of problems. Make sure device hardware, a device firmware that resides on the hardware, those versions are compatible. They need to be compatible and up to date. Generally, the major revision, which is the first number that you find in your firmware variations, has to be the same across all devices you expect to work together on a network. And finally, again, to come back to where we started from, make sure all your cables are good and your connectors. Some useful tools that you might want to know about. Again, we kind of mentioned these applications already. If you're working on Shure network devices, make sure you have the Web Device Discovery application, the Update utility for keeping your firmware up to date, and for those devices that are compatible with it, Wireless Workbench 6. If you're working on a Dante network, Dante Controller and Dante Virtual Sound Card are two really useful pieces of software available from Audinate. And just general networking, Wireshark, which allows you to monitor network traffic and maybe determine where some problems might be happening. And IP scanning tools like Angry IP or Advanced IP that actually, if you have a bunch of devices on your network and you don't know what those IP addresses are, these tools allow you to go out and pull every IP address of everything on your network and maybe identify a conflict that you didn't know was there. Some useful things there. Upcoming training events, you can always find it at shure.com/training, future webinars, other e-learning modules, good stuff like that. And I know we're almost out of time here, but Cheryl, any questions we might be able to tackle?
Yeah, we're very short on time, so we're not going to get to all of the questions. So first of all, many apologies if we don't get to your question. If it's still burning a hole in your brain, you can always send questions to support@shure.com. We got a great team of people here that can answer a great many questions. So support@shure.com if we don't get to your question. So let's start with this one here. We have several Shure products that we often network. Most work fine, but we often have trouble getting UHFR to talk to Workbench over the network. Is there something different about UHFR that makes things difficult?
Why, yes, there is. This is a great question, and I'm sure a pain that lots of users feel. UHFR was one of the first properly networked wireless systems that Shure ever made. And
The first.
The first?
The first.
So first, in fact, that it has Ethernet and USB networking. What's different about UHFR, though, if you compare it to the rest of the contemporary wireless gear that we have that's networked, is that it speaks a protocol that was actually homebrewed by Shure. This protocol worked fine in the early 2000s when it was developed, but to be honest, it doesn't really scale to with the robustness and reliability that the newer networking protocol of all of our other wireless devices uses. It still works fine. We still recommend it for production uses, but what users can tend to see is that if you've got a bunch of ULXD or QLXD or Axient or anything like that alongside UHFR, if there's going to be a networking issue first, it's going to happen with UHFR devices. Some recommendations I would make to get the best use out of networking UHFR is to always use star topology, to use DHCP whenever possible, to ensure that you have a wired connection, your computer's hardwired to your network. Whenever possible, wireless connections just introduced a host of new issues and variability in the robustness of your connection. And then to get familiar with some basic tools like ping, if you use terminal or the command line, to ping a device is to send a very light message to its IP address confirming connectivity. And oftentimes, just simply pinging a device from your computer can ensure that there is connectivity or not. And if there isn't, it isn't the UHFR's fault or anything else's fault. It's the connectivity of the network that could be there. So I hope that answered the question.
All right, one more really quick, and then we're going to have to wrap it up. I've seen many users depending on the Crestron control subnet to handle DHCP on the Dante Shure network. I've heard mixed reports that the Dante traffic will cause problems with the Crestron control subnet network and vice versa. Have we observed this at Shure, and do we have any recommendations?
Boy, how do I make this a short answer?
It's a specific question, that's for sure.
It is a specific question, and I can only answer it anecdotally, which is yes. We have seen issues with that, and we have not yet quite pinned down what the source of those issues are, but there's something about the way the Crestron DHCP server works that seems to be causing issues on some Dante networks, and I'm sorry that I don't have a specific answer for that, but I've just, again, anecdotally, troubleshooting situations where the Crestron DHCP server is removed and everything starts working again. And that's about as much detail as I can say, other than like that is an observed behavior that we've seen multiple, not just one time, like we've seen that happen multiple times. And that comes to, I guess, kind of maybe a point we can sort of wrap on here. And again, sorry we didn't get to everybody's questions, is often just swapping out devices makes a big deal. Oh, you're having network problems? Do you have another switch? In fact, that's something we recommend everybody have in their toolkits. We used to always say, make sure you have a multimeter and some headphones with you. Now, carrying a spare 4-port gigabit network switch in your tool bag is not a bad idea. Often you can break things down to just a small network and be like, okay, this works, right? So I know that I know the hardware works because I'm connected to my own little switch that I know always works, and this is good. So having that with you to swap out in place of another switch or router is not a bad idea. Sometimes, I know it's a pain to carry 2 computers, but oftentimes when you have discovery issues, there's so many things that can vary on computers. There's so many different things, settings, firewalls, antivirus, especially if the IT department locks down your computer, that might prevent discovery of devices. Sometimes just simply trying another computer and then, oh, look, there everything is, and it's just because there's some little setting on a computer that, couldn't get there. Again, it doesn't happen often, but it does. So having spare devices, not just cables. Of course, you should always have some extra spare cables with you, right? But beyond that, a spare, like I said, a little network switch, some other way of connecting sometimes just works. So besides turning it off and back on again.
Awesome. We want to thank you so much for joining us today. We hope you learned a little something, and we hope to see you next time.